One of the applications that's very commonly occurring when dealing with hyperbolic functions is the idea of hanging cables, or what's sometimes referred to as catenary curves. Now, we won't often use this language. In fact, we'll pretty much never use it except for exactly this moment. But we will see these sorts of curves being used in a lot of Chapter 2 content. So let's take a look at what we have. We'll say that hyperbolic functions arise when a homogeneous cable is suspended between 2 points. That is, this red curve here can sometimes be modeled by these sorts of hyperbolic functions. Specifically here, you could probably guess that this cable looks like some modification of the hyperbolic cosine function, which we saw its graph of many videos back. So if I take a look down here at example 4, I can imagine the following. Suppose a cable is attached between 2 poles. Poles maybe stand 30 feet apart, and I can model it by this function, hyperbolic cosine of x plus 5. I want to determine the exact length of the cable as x goes from 0 to 10. Okay, if I was to go ahead and actually do this, I can see here that if I'm interested in trying to find the exact length of the cable, I'm doing an arc length question. That's not difficult. But I do have some conditions to check. Do you remember what the condition was in order to be able to use that arc length formula we established many sections back? Well, it had to do with my function needing a continuous first derivative. So I'll start by saying we see that y prime is going to be, well, let's see, the derivative of hyperbolic cosine is hyperbolic sine, and of course the derivative of my 5 is just 0. So hyperbolic sine, is that a continuous function from 0 to 10? If we were to go all the way back to the pictures that we had for hyperbolic sine, we were able to see that, yeah, that definitely was a continuous function. At least it appeared to be one. And when we looked at the formula for hyperbolic sine, we saw that it was built from continuous functions. So very, very clearly, this is going to be continuous on the interval from 0 to 10. And so it's not difficult at all to start to set up the arc length. I know that my arc length would be computed from 0 to 10. And remember, it was the square root of 1 plus my first derivative squared. Now, if this is an integral that I have, and I'm actually required to evaluate this integral, I might need some additional machinery to help me simplify this. Please make sure that you're careful with this and notice that you cannot simplify this down to something like 1 plus hyperbolic sine of x. You can't square root each piece underneath one of these radicals. That never works, or at least it only works in the most obscure of cases. So I need to go ahead and think about something else I can do with this, because at the moment, this is really awkward. Well, it's at exactly this moment where identities can start to become really valuable. I mentioned several videos back that identity 3 was the only identity that we really might need to know. It was that kind of basic identity. You might recall it said that the hyperbolic cosine squared of x minus the hyperbolic sine squared of x was equal to 1. Well, with this in mind, what can I go ahead and replace 1 plus hyperbolic sine squared with? Well, I should be able to go ahead and replace it with hyperbolic cosine squared. Right, of course, I should be able to get that by just adding that hyperbolic sine squared to the other side. Now, when I get here, I can simplify a bit further. Notice that I'm going to be able to simplify this down pretty nicely. What's the square root of the hyperbolic cosine squared? Make sure you include absolute value of the hyperbolic cosine. However, if you think back to the picture of the hyperbolic cosine, we can make a quick note here. Wasn't the hyperbolic cosine graph always positive? Hyperbolic cosine of graph, or cosine of x, is always positive, right? I mean, think about what the picture looked like. So because of that, I can simplify this down to just being hyperbolic cosine of x. Well now, since this is a continuous function, I can use fundamental theorem of calculus, and I can say, what's the antiderivative of the hyperbolic cosine? Well, I know that should be the hyperbolic sine of x, and I just evaluate from 0 to 10. That would be hyperbolic sine of 10 minus hyperbolic sine, hyperbolic sine of 0. Now you might recall that what we said in one of our very early videos is that sometimes we will simplify these values down if they do this nicely, and other times we'll just leave these values in this kind of hyperbolic sine of a number form if they don't simplify nicely. Now we actually showed a while back that the hyperbolic sine of 0 is indeed just the value of 0, whereas the hyperbolic sine of 10 is going to be pretty darn ugly. So I'm just going to go ahead and leave my final answer here as hyperbolic sine of 10. This part here, remember, turned into 0. So there we go. We actually found the exact length of the cable. And if I wanted to go ahead and get like a decimal approximation, there's nothing wrong with saying that I know that this is equal to e to the 10th power minus e to the negative 10th over 2 and getting some sort of a decimal approximation from the calculator. That's fine, but if I'm able to stop earlier and stop at this point, you're more than welcome to do so. So hopefully this gives you a sense of how these functions might show up in a regular Chapter 2 question. If you take a look to kind of end this video, down here at example 5, you'll see that example 5 has a bunch of different parts to it. It's got 3 parts total. You can kind of imagine this as like a mini worksheet for the section of 2.9. There is no large worksheet. There's no worksheet posted that you'll find up in Blackboard. So this will show you kind of how these functions can be integrated into the ideas that we've covered so far. So notice here, in this example, I'm working with a region that's bounded by some curves that include a hyperbolic trig function. And I say, find the area of the region. So like a 2.1 question. I say, find the volume of the region when you revolve it around the y-axis. Again, I'm dealing with like a 2.2 or a 2.3 question there. And I just happen to have one of these functions in the mix. Down here, I ask a question about, suppose I rotate this curve around an axis, attempt to determine the surface area. Why is this integral not going to give me the surface area? You know, like what's wrong here? But all of these are questions related to earlier in Chapter 2. And hopefully, by completing these questions, you'll get a good sense of how these functions might be integrated into the content that we've already covered thus far in this class.